Hey everybody, Ben Voorhees here with Adams Corp. I'm the Training and Service Manager, and today is the first video in a series of videos that we're going to make going over different lighting concepts. Most of the time, the people that we're dealing with are very strong software engineers or controls engineers and understand once they get reliable data, how to manipulate it and get the decisions out of that data that they need, right? But one of the things that is commonly misconstrued is image formation when you're dealing with visual inspection, automated visual inspection, that is. So if you're not getting repeatable data into your software, into your system, then it doesn't matter how good you are at manipulating your software or your data, you're never going to get repeatable results. So one of the things that we want to try to attack with this series of videos is bad image formation. We want to get rid of that, and we want to give you guys the tools to do that through these videos by highlighting a few key little things that you can do to make your application more robust, so you can get more repeatable information going, images going into your software. So today what we're going to be talking about is collimated lighting. What is collimated lighting? Well, simply put, collimated lighting normally is coupled with backlighting. So everyone knows what backlighting is, right? It's where you shine a light behind your object directly towards your sensor, and it silhouettes it or outlines it. So this is used for a lot of applications. The main ones being if you want to silhouette or outline a geometry and then measure or gauge different things. That would be one way to do it because it creates really nice contrasted edges on the outer section of parts. The other thing that it can be used for is to look for like particles, or foreign debris and things like that. Tiny little pieces maybe that are in a liquid or a fluid or on some sort of clear substrate or something like that. You might want to backlight those, and the particles or the anomalies will block that light, and you'll be able to see the silhouette of them and see their size and everything else. Now, one thing people don't talk about when you use backlighting is the fact that light tends to be sort of sticky. It's all encompassing. It wants to wrap around things. It wants to grab and move, and almost like water in a way sometimes. It's sort of a weird analogy, but you'll see what I mean in a minute. So let's say you're using a backlight and you have a panel light like I'm showing you there. That panel light will shine light in all different directions, totally random. So you will have some rays coming from the very right hand side of your backlight, or the very left hand side of your backlight at a steep angle, and wanting to hit the object that you're illuminating and trying to silhouette, and especially like curved geometries and edges, it'll want to wrap around and grow around those edges, fuzzying the edge, making the edge not easily discernible, right? And the whole goal of machine vision, especially with respect to image formation, is we want clear, clean, concise binary lines between the data you want and the data you don't. So how do we use collimated lighting to make backlighting more effective, right? Well, we already know that light, especially backlight on a panel, wants to crawl around your object. How do we stop it from doing that? Well, one way to do that would be to direct the light so that the light is shooting out from the plane, right, that you were using, or the panel, shooting out totally normal, right, or perpendicular to that plane. If that happens, then the directed light will want to pass straight by the edge rather than grabbing that edge and wrapping and growing around it. So I have an example set up for you guys today that I wanted to show you. And as you can see here, right, and you were probably wondering why I was glowing red in my cameo there, is because I have a red backlight set up here underneath an Insight 7000 Gen 2 Cognex camera. Got a regular 35mm C-mount lens, nothing special. And a lot of times if you want to get rid of perspective and get more crisp edges, you might use a telecentric lens, but this is just a quick down and dirty setup. So as you can see here, I've got my red backlight. I've got my camera, or my imager or sensor right here, with the lens directing light back onto that sensor. And then I've got these blocks kind of holding this piece of collimation film okay, over top of the backlight. So collimation film does exactly what you were seeing in those graphics, which is directs the light in a straight, normal fashion directly straight up from this light. So there aren't rays coming from the top and coming from the side and shooting at weird angles. They're coming straight normal or perpendicular to that plane. Now you can see down here I only covered half of the object with this collimation film. Okay, so what does that mean? That means that the light here is coming out in a totally random fashion, and it's kind of diffusing and going all over the place, right? Totally random. So even some rays are going to be shining from here and going straight across. Some are going to be shining from here and going straight across, and some are going to be going straight up, just like collimated rays. Anyways, what I'm going to do is I've got a couple of parts here. One of these is an Allen wrench, right? So it's just about, I think it's a hexagonal shape. And I'm going to use this to put it on here and observe some of the things that are happening and what the light's doing and how we can use the different styles of light, collimated and uncollimated light, to inspect this. And also a little cylindrical plastic piece. We're going to see what that looks like under the light, and what kind of image are we getting out of this sensor between collimated and uncollimated light on the top and bottom. So without further ado, what I'm going to do is open up our software here, blast it out, and then on the bottom left I'm going to keep a nice little view of our test area, and let's see what results we can get to show up in the software, right, as data, and how are we getting better data, more repeatable data, more accurate data to what's actually happening down here in real life, right? Because that's really all we're trying to do here when you're taking an image. You want your image to most accurately represent what is real life or really happening, so that you can get process control of what's happening in your plan. So the first thing I would want to do is maybe I'll take this hexagonal wrench and I'll put it across here. All right, so as I lay that hexagonal wrench across there, you can see half of that wrench is over top of the collimated area. The other half is on the uncollimated area. So I go ahead and take an image, right? So we can see this this pink datum here denotes the portion of the backlight on top is collimated, on the bottom is uncollimated, and what are the different types of images we're getting. So first off, I think it's pretty obvious what's happening, right? So I've got the collimated measurement across the width of this Allen wrench, and then I have the uncollimated width measurement across this Allen wrench. And the first thing that should jump out at you is, hey, that flat portion up top that creates a sharp edge down here, that looks dark with both collimated and uncollimated. Because at the end of the day, backlighting will silhouette things properly, and I'm not saying you always need collimation. But this is a prime example when collimation can make or break your application completely. For instance, those more chamfered or almost countersunk style edges that angle downwards from this top flat, you can see those are highlighted very well by the collimated light. All right, why is that? Because we have our light rays shooting straight up past this crisp edge, and they're not coming in from the right hand side and wanting to grab and wrap around this. Now conversely, in the uncollimated side, look at what's happening, right? Down here, we're losing our edge, right? That light wants to grab, stick, and wrap around this part so much that you're losing an edge completely, and you're getting an incorrect measurement, let's say. Now, normally what we would do is calibrate this and give a real world measurement in millimeters or, inches or whatever. I mean, for now, I'm just using pixels, okay? But you can see the actual measurement of this wrench, likely the width of it, would be closer to 121 pixels. All right, we're getting down here, because we're using uncollimated light in this application, closer to 70. I mean, that's 50 pixels, or in this case, almost 100% error, right? 90% or something like that. So What a great way to use collimated light to get more accurate data and sharper edges. If you zoom in, this is really when you're talking about machine vision where the rubber meets the road. Right here. Where does that edge created? And as you can see on the collimated light, the edge we're looking at here is maybe a 2 to 3 pixel edge gap there, right? But if you look down here, it's this huge region of edges, that creates more of that inaccuracy in your system, right? So what a great example of when to use collimated light. Now that one's a little more obvious because it's kind of dealing with sharp angles and things like that, but I wanted to put something cylindrical on this. So as you can see, I have the bottom part of my cylindrical part hanging off of the collimation film, and the top part is hanging over. And I'm going to give this another trigger. Now here's where it gets a little bit more insidious, right? That with the Allen wrench, because of those the angular shape of it, was a little easier to see. This right here, it's a little bit duller because it's a constant curvature going around something cylindrical. So let's take a look at the edges here. So we got about a 131.9, closer to 132 pixel width on this part, whereas the uncollimated light is closer to like 102. So we're seeing maybe like a 30%, 20% error in the measurement here. Now, why are we seeing that error in measurement? Well, as you can see with the collimated light, again, we're getting maybe 1, 2, 3, like a 4 pixel edge width, maybe, right around there. So that 4 pixels is what the software has to work with on where to draw that edge. That's almost the error you can expect in the system, right? Because of the type of image you've created. If I zoom down here into your uncollimated light, look at how much that wants to wrap around the edge of this part. Right now, instead of like 3 or 4 pixels, you've got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. You have more than tripled the error in your system by using uncollimated light if your objective was to measure the width of this part. So, really machine vision, the nuts and bolts of it, as you're trying to understand how the software works, it is down at this level, at the pixel level, and understanding your image at the pixel level is of paramount importance, especially when you're trying to gauge to a specific tolerance or something like that. So you want to avoid scenarios like this with really gray or gradual edges, and you want to try to elicit more strict, hard edges like this. It'll give your system much better results. It'll give you more accurate readings, and it'll give the software something repeatable that it can latch on to. So, how do we avoid those edges, those gray areas, those sort of fuzzy transitions in our machine vision applications? Well, a lot of times it's lighting and lensing. In this case, we're using collimated lighting, collimated backlighting specifically to create a more crisp edge for a more accurate measurement. And a small thing like that, an inexpensive addition by either buying collimation film or specifying a light that already has collimation film built into the face of it, into the panel, which exists at all your major lighting providers as an option. So small things can add up to create efficiencies or inefficiencies in your machine vision application. So this is just one example. I'm looking forward to seeing you guys again and discussing something else. But for now, please, as usual, like, subscribe, and please let us know if you have any machine vision applications that you want us to take a look at. This is all we do. Thank you very much.